In this video, I'm going to talk about reaction mechanisms and how we can use them to get information about the rate law here. Okay, so these reaction mechanisms are just these sequence here of these bond making and bond breaking steps that occur in a reaction. Basically, it's just the process by which a reaction actually occurs. So anytime you hear reaction mechanism, just think, okay, that's talking about the process by how the reaction itself takes place. We know that the balanced equations do not explain how the reaction occurs. They just show us what we start with and what we end with and the amounts of each. All right, but you need to realize here that most reactions are not just one step processes. Okay, it's not just going to be that this becomes this and it happens in one step. All right, many reactions here are actually a sum of a series of steps. You still have the same reactants and products, but it actually has a bunch of steps that take place in order to get there. This must be determined by experiment, and it has to agree with the overall stoic and the experimentally determined rate law. All right, so you can kind of propose a mechanism here, but in order for the mechanism to actually work, it has to agree with the stoic and it has to agree with the experimentally determined rate law. Okay, so again, these reaction mechanisms that we're talking about are just a series of steps here that show you how a reaction takes place. So if you notice here, this could be a potential mechanism. They have a series of different reactions, and you'll see that they even tell you whether the step is fast or slow. And we're going to talk about all this as we go forward here. An elementary step is a reaction that occurs in a single step. So a reaction mechanism could be made up of a bunch of elementary steps, okay? These are just reactions that occur in one step. A couple terms here. If you hear the term molecularity, this is talking about the number of molecules that are participating as reactants. So if you have a unimolecular reaction, that's when you have a single molecule collision that's just causing the reaction to take place. All right. Bimolecular would be when you have two reactant molecules colliding, and termolecular would be where you have three reactant molecules colliding at the same time. This would be very rare here. So if you're looking at this table here, you can see if you have just one reactant by itself, that would be unimolecular. If you have A reacting with A, well, that would be two different molecules. So that would be bimolecular. A reacting with B, that would be two molecules here. So that would be bimolecular, and so on here. All right. So anytime you hear this term molecularity, it's just talking about the number of molecules that are participating as reactants, and you might have to identify it as unimolecular, bimolecular, or termolecular. Remember here that an elementary step is a reaction in a single step here. It is very important you understand what an elementary step is. We already know that you cannot determine the rate law from the overall stoichiometry of a reaction. We already talked about that. You cannot do it. However, if you have an elementary step in a mechanism, you can predict the rate law for that elementary step. All right, very important here, because now what happens is people start confusing and forgetting what we previously learned. You cannot predict a rate law from an overall balanced equation. But if you have an elementary step, you can write the rate law based on the stoic of that elementary step. All right. So for example here, if you have an elementary step where you have A in a unimolecular reaction becoming the products here, if this is an elementary step, we know that there's just one reactant. So the rate law for this would be rate equals K times the concentration of A raised to the power of 1, because there's just one of A there. All right, so notice we were able to write the rate law and we knew the order with respect to the reactant because it was an elementary step. You can write the rate law based on the stoic of elementary steps, but you cannot do that on an overall balanced equation. Again, we could do this with, if we had A plus B going to products here, this would be bimolecular. Because this is an elementary step, you just look at the reactants, you can write the rate law. Rate equals K times the concentration of A times the concentration of B, both raised to a power of 1. They'd both be first order because of the balanced equation tells you there's just one of each. And you can see how the rest would work here, how you could even have like 2A reacting with B. If this is an elementary step, the rate would be K equals concentration of A squared times the concentration of B. All right, so as long as you have an elementary step, you can write the rate law for that step, for that reaction, based on the balanced equation of that elementary step. But you got to remember here, you cannot still write the rate law for an overall balanced equation using the stoichiometry. You can only do this for an elementary step. So we already know what reaction mechanisms are. It's just the process by which a reaction takes place. If you have multi-step mechanisms here, that means you just have multiple elementary steps here. Basically, all these elementary steps must add up to give you the chemical equation of the overall process, the overall reaction that takes place. A lot of times what happens here is we have intermediates forming. All right, you definitely need to know what an intermediate is and be able to identify them in these mechanisms. Basically, an intermediate is a substance that is created in a mechanism, but then it's consumed, it's used up. All right, so it's created, it forms, and then it disappears. It's not a reactant, it's not a product, it actually cancels out in the mechanism. That's key. It's not there in the beginning, it's formed, and then it's used up, it cancels out. That's an intermediate here. All right, so let's go and look at this example. It says here we have ozone going to oxygen in a two-step mechanism. So we see O3 breaking down to O2 plus O, then we have O3 plus O going to 2O2. All right, so each of these steps, because this is a mechanism, would be an elementary step. All right, so that's very important here. So the first question we have here says, describe the molecularity of each elementary step. So if we look at the first one, all we have as a reactant is O3. All right, so that's just one molecule. So that step would be unimolecular. If we look at the second elementary step, we have O3 plus O. There's two substances involved. So this would be bimolecular. All right, so you need to be able to identify the molecularity here of any of these elementary steps in a multi-step mechanism. Now we want to write the overall reaction from this multi-step mechanism. Essentially what you're doing is you're just adding up and canceling out your elementary steps here. So essentially what we're doing here is any substances that are the same on opposite sides of the arrows, okay, in different steps would cancel out. All right, so for example here, do you see how we have O here, just O, on the right side of the first elementary step, but then on the left side of the arrow in the second elementary step, we have O as well. Well, they're on opposite sides in different steps, so they would cancel out here, okay? So that's going to cancel out. Notice the O3s here are on the same side of the arrows on in both elementary steps, so they would add together. So it doesn't look like I can cancel anything else out. So when I add these up to write the overall equation, I'm going to have here two O3s on the left side of the arrow going to three O2s total when I add them up on the right side. That would be the overall reaction here. I canceled out whatever I could, and then I wrote the overall equation. It should be balanced now if I did this correctly. So remember, in order to do this, you're just adding up the elementary steps. Any substances that are in different elementary steps on opposite sides of the arrow could potentially cancel out here. So this would be the overall reaction for this mechanism. The last part of this question wants us to identify the intermediary. Remember, the definition here of an intermediate is a substance that is created, then consumed in this multi-step reaction. It's not a reactant or a product. It cancels out. Be careful, it's also not a catalyst, all right? A catalyst would be there in the beginning, there in the end, and it would cancel out as well. But the difference is for an intermediate, the intermediate is not there in the beginning, it forms, and then it is used up and cancels out. A catalyst would be there in the beginning, there in the end, just to make the overall reaction go faster and then cancel out. So that's very important. We saw when we did the overall reaction here, we canceled out the O. It wasn't there in the beginning, so it was formed, and then it was used up. So the intermediary here would be the O. All right, so very important to understand the difference between an intermediate and a catalyst in these mechanisms. Now we want to look at the rate determining step. The slowest step of a reaction, the slowest step of a mechanism is the step that determines the rate. All right. If every reaction here is made up of these series of elementary steps, the rate laws and speeds of those steps will determine the overall rate law. But realize here, it's kind of like we have a limiting reactant, but with a rate law. The slowest one is going to be the one that determines the overall rate. You can't be kind of faster than your slowest step. Each step, each elementary step in a mechanism would have its own K and its own activation energy. All right, typically here in a mechanism, one step is slower than the others, and the slowest step is the one that's going to determine the rate law for a reaction. All right, very important to understand that this still must be determined via experimentation. You still have to determine the rate law from experimentation, but realize here the slow step is going to give you the rate law here in a mechanism. Remember, if you have a mechanism and you have elementary steps, you can write the rate law for an elementary step. So if you have a slow step, you can write the rate law from that slow step because you know the rate law is going to be based on that slow step. But again, you have to confirm this with experimentation. So if you notice here, this particular mechanism right here, all right, you can see the two steps that it takes place by. You have a slow step and then a fast step. Realize here that this slow step, this first step, would be the rate determining step. When the slow step is the first step, this is the easiest of the ways to determine the rate law here. If your slow step is your first step, you just use the molecularity here. Use the coefficients in the elementary step of the slow step to write the overall rate law. Okay, so if we just let's look at an example here. If here's my overall reaction, okay, that's the overall reaction that we're looking at. And the rate law is determined to be, from experimentation here, rate equals K times the concentration of NO2 squared. All right, that's what it's determined to be via experimentation. Now we want to look at this mechanism to see if we can confirm this rate law. So if you notice here, all right, there's two steps in the mechanism. Each of these steps is an elementary step in the mechanism. The first step is slow, the second step is faster. Remember, you can determine the rate law from the slow step. And since the slow step is first, this is very easy. All you do is write the rate law based on that first step, based on the overall stoich of that first step. Remember, you cannot do this. You cannot write the rate law for an overall balanced equation, but if you have an elementary step in the mechanism, you can write the rate law using the stoich for the elementary step. And because the first step is slow, that's going to be the one we're going to write the rate law for. So if we did this, we would have rate equals K times the concentration. If you notice here, the only reactant I see in that slow step is NO2, and there's just two of them. All right, there's two NO2s. So essentially, it's going to be rate equals K times the concentration of NO2 squared. And I'm able to do this because that is an elementary step. And if you notice, that is the rate law that was determined via experimentation here. So they match. This could potentially be the mechanism that this reaction takes place by. So anytime the slow step is the first step, you can just write the rate law based on the stoichiometry, the coefficients there of the reactants in that slow step. And we can do this because that's an elementary step. What if the slow step is not the first step? Okay, so you're going to write the rate law for the slow step, then it's just a little bit more work. Usually it involves some substitution here. So let's just say this is our overall reaction. We have 2A plus 2B going to C and D here. And the rate law that's determined via experimentation is rate equals K times the concentration of A squared times B. All right, here's the possible mechanism. It's three steps. Notice the slow step, though, is the second step. It's not the first step here. So it's going to be a little bit more work. We can write the rate law based on the slow step. But when it's not the first step, there's a little bit more work here. All right. So the first thing we're going to do is write the rate law for the slow step. So for that slow step, our rate law would be rate equals K. All right. This is an elementary step, so I can write the rate law based on the molecularity here, based on the coefficient. It'd be K times concentration of X to the power of 1, because there's just 1, times the concentration of B. All right. Again, that's the rate law for the slow step. All right. But if you notice here now, we have X here in our rate law, and X isn't even part of the actual reaction, right? And this happens here partly because the slow step was not the first step here. So what we know from the first step now, if you take a look at the first step, we can see that A plus A is in equilibrium to get X. So essentially here, from step 1, we know that the concentration of X would be equal to the same thing as the concentration of A squared. Okay? Do you see how we kind of just looked at the first step here and said, oh, well, A plus A gives us X. So the concentration of A squared would be the same thing as the concentration of X. So basically, you're just going to substitute in now. So when we do that, we get rate equals K. X would be the same thing as the concentration of A squared times the concentration of B, which is still there. So that would be the actual rate law for this particular mechanism, and it does match the rate law that was predicted here from the experimentation. So again, if the slow step is first, you can just write the rate law based on the coefficients of that first step. If the slow step is not first, you usually have to do a little bit more work and do some substituting in, but you still can get the overall rate law here. It's just a little bit more work. All right. So you need to realize that the reason why we can write the rate law from these steps is because they're elementary steps. We still can't write the rate law from the overall balanced equation. Let's look at another example here. It says the experimentally determined rate law for a reaction is rate equals K times the concentration of NO2 times the concentration of F2. A suggested mechanism for the reaction is seen below, and we want to write the overall reaction, okay, and determine if this is an acceptable mechanism here. All right, so the first thing we need to do is, if we're doing the overall reaction, we have to add these up. All right, remember, anything on opposite sides here of the arrows in different elementary steps could cancel. So I see that F is present on opposite sides in each of the steps. So that's going to cancel. It doesn't look like anything else is the same. So when I add these up here now, realize that I have two NO2s on the left side. So it's going to be 2 NO2 plus F2 going to 2 NO2Fs. All right. If I check this, it should all be balanced. That would be the overall equation here now. And then it also says, is this an acceptable mechanism? So if we look at the slow step, it's first. So if we write the rate law for the slow step, we have rate equals K times the concentration of NO2 times the concentration of F2. Remember, we're just writing the rate law for the slow step, and we can use the balanced equation, the stoichiometry here, to get the orders, because this is an elementary step. And when I write this rate law, it does agree here with the experimentally determined rate law. Notice, if you tried to write the rate law from the fast step, you would get a totally different rate law. All right. Just keep in mind here, you have to write the rate law from the slow step in the mechanism. I just want to talk a little bit more here about catalysts. Remember, catalysts are the substances that increase the overall speed of the reaction, but they don't undergo a permanent change. They lower the activation energy, but they don't change the overall energy of the reaction. All right, that's very important. They lower the activation energy, but they don't change the overall energy. They do provide an alternate pathway here. So it's important to understand that catalysts lower the activation energy by providing an alternate pathway. They kind of do both things here. Basically, this usually results in a higher percentage of these effective collisions. So we get a faster rate here of the reaction actually taking place. Remember, catalysts are present in the beginning and they are still there at the end, and then they cancel out here in the mechanisms. Intermediates are created and then used up, but both of them are not included here in the overall reaction. So very important to understand that these catalysts speed up the reaction by lowering the activation energy, providing a different pathway for the reaction to take place, allowing these effective collisions to occur much more readily. You definitely need to understand catalysts here by looking at graphs like this. So we have potential energy here on the Y and the reaction progress here on the X. Notice you have your reactants. All right, this is where you're starting in terms of your energy, and then it takes a certain amount of energy, and then eventually those reactants become the products here. All right, the green line is the uncatalyzed reaction. If you notice, this is your starting value here for your energy, and it takes this much energy here. The activation energy will go all the way up to the peak of the green. That's something important to pay attention to. The activation energy is not from 0 to the peak. You have a certain starting energy in your reactants. So the activation energy is the amount of energy it takes to go from your starting energy of your reactants up to the peak here. All right. So it takes a certain amount of energy in order to get those products to form. But notice in the red, the catalyzed reaction, you start in the exact same area. You end in the exact same area. The only difference is, right, it takes less activation energy in order to get that to take place. All right. So the activation energy here again goes from this starting value of the reactants up to the peak. All right. It's not the entire line. All right. But the difference here in energy, this delta H, is the difference between the reactants starting energy and the products energy. If you notice, even with the catalyst, the beginning and ending energy is the same. So the difference, the overall delta H here, or the delta E, the change in energy, doesn't change. What changes is the activation energy is lowered. So you should be able to look at a graph like this, be able to understand which one will be catalyzed, which is uncatalyzed, maybe determine the overall energy change, determine the activation energy here for each. Definitely something you need to be able to look at and understand here. We want to look at something here called the Arrhenius equation. This is basically how we can determine the activation energy, and it relates this idea of the rate constant and temperature to help us determine the activation energy. Now, you don't have to memorize this equation. We shouldn't really even have to use this equation on an AP exam at all. The key is understanding the ideas here behind this equation to be able to figure out the activation energy. So you can see here what all the letters mean. K is the rate constant. A is this collision frequency factor constant. EA we know is the activation energy. R is the gas constant here, but notice it's a different version, different units here of the gas constant. And T is the temperature in Kelvin. So again, we should not need to memorize this equation. We don't even need to use this equation. This is the big takeaway here. All right. This is what we can kind of do here to determine the activation energy. Basic gist is this. If you do an experiment multiple times at different temperatures, that's key. We know if you change the temperature, you change the rate constant. So if you run an experiment at different temperatures and measure the rate constant, okay, so we're doing an experiment at different temperatures measuring K. If you plot the natural log of K versus 1 over the temperature, all right? Because remember, you did this multiple experiments here. So you have multiple data points for K and temperature. If you plot the natural log of K versus 1 over temperature, that's not time, all right? The slope of that line is equal to negative EA all over R. All right, so you find the slope of that line, put it equal to negative EA all over R, and you can solve for the activation energy. That's the big takeaway here. Not using the equation, understanding that you run an experiment at different temperatures multiple times, measure the K value, determine the K, the rate constant, plot the natural log of K versus 1 over temperature, the slope of that line is equal to negative EA all over R, and you could solve for the activation energy. Being able to explain this, how you could find the activation energy, is very important. Perhaps even labeling the axes here of the graph and explaining how you would get to the activation energy is also very important. So this is a pretty big idea here for AP, and you need to understand how we're determining that activation energy. Realize here that K will increase with increasing temperature. That makes sense. If you increase the temperature, you'd be increasing the rate. K is going to go up here, but K will decrease with increasing activation energy. It's opposite. Think about that logically. If the activation energy is greater, it's going to take more energy to get the reaction to occur. The overall rate is going to be slower, so K is going to drop. All right, so that's definitely something you should understand here as well. But the big takeaway here from this slide is understanding this idea right here. All right, running an experiment at different temperatures, determining the value of K for each of those experiments, plotting the natural log of K versus 1 over the temperature. The slope of that line is equal to negative EA all over R, which would allow you to find the activation energy here. Don't know this equation. Don't worry about doing math with it. This is the big takeaway here, understanding that idea. I just want to talk a little bit more here about catalysts. If you ever hear the term homogeneous catalyst, we know that homogeneous mixture means it's all uniform. So it's kind of the same idea here. If you have a homogeneous catalyst, the catalyst exists in the same phase as the reacting molecules here. So for example, chlorine gas, which could come from these chlorofluorocarbons, these CFCs, can catalyze the decomposition of ozone in the atmosphere. They're both in the gaseous state. So the catalyst is a gas and the molecule it's reacting with is a gas. All right, so you can kind of see that here in this picture. This is not something you would need to memorize, but it's actually pretty interesting. They used to use these chlorofluorocarbons, but then what they found is that these chlorofluorocarbons were actually contributing to a breakdown in ozone in the atmosphere. So UV light would actually cause a chlorine to break away from one of these chlorofluorocarbons. That chlorine would then hit a molecule of ozone, all right, essentially breaking it down, all right, pulling away an oxygen. And then in the process here, what happens is you get another free oxygen that can hit that ClO molecule, right, which forms O2 gas. But then now you have another kind of free chlorine, which will come back and hit another molecule of ozone, breaking it down. So it's kind of like this process would just keep happening, right? So when this UV light hits these chlorofluorocarbons, the free chlorine would kind of break down the ozone, but then you'd get more free chlorine to break down more ozone in the process. All right. Again, this was how the ozone layer was kind of depleting here. But the understanding here is that a homogeneous catalyst is that the catalyst is in the same phase as the molecule it's kind of reacting with. Heterogeneous catalysts then are just when the catalyst exists in a different phase from the molecules it's reacting with. So this would be like in catalytic converters here. They have platinum, which promote the conversion of these poisonous gases from the exhaust, CO, NO, and NO2, into less poisonous gases, CO2, H2O, and N2 here. So essentially the platinum is a solid and it's reacting with gases. So this would be a heterogeneous catalyst. Again, not something you need to understand this entire process of the catalytic converters, but understanding here that these poisonous gases are going through that and being converted into less poisonous gases. We know that there's an issue with CO2 and global warming, but just understand this idea that a heterogeneous catalyst would be in a different phase from the molecules it's reacting with. Little review of enzymes here. We know that enzymes are essentially catalysts. It's just that, you would look at enzymes more specifically in biology. They're made of proteins. You have the reaction being catalyzed at this active site with this like lock and key kind of model here, where the substrate or the compound kind of undergoing the reaction at the active site. So the substrate kind of fits in to the active site of the enzyme. The enzyme kind of positions everything perfectly, makes the reaction happen faster so that you can get your products forming essentially. Again, this is just kind of more for your information, kind of bringing in the biology kind of parts here, talking about catalysts and enzymes. We want to make sure we understand these reaction coordinate diagrams. We've kind of seen these kind of throughout the notes here, but we want to make sure we're good with this. So we're going to have energy here on the y-axis, and then the reaction coordinate or the progress of the reaction along the x. So you can see in this particular reaction, our reactants are always what we start with. There's some kind of activation energy needed, and then it kind of drops back down, and then there's kind of more activation energy, and then it drops back down, and eventually you get your products. So you should be able to look at this and say, okay, my reactants are here. This would be the energy of my reactants. This would be the energy of the products. The products are lower than the reactants, so energy was exiting. So this would be an exothermic reaction, all right? The ending energy here of your product is lower than what you started with, so that would be exothermic. But realize here, these peaks or these humps here in the graph can tell you some information about the mechanism here. All right, we know that this would be a two-step mechanism. Essentially, there is two separate speeds here, two separate humps. There's a first hump that requires some activation energy, and then a second hump that requires some activation energy. Remember, in these mechanisms, each step, each elementary step in the mechanism has its own K and its own activation energy, and you can see that from here. So the number of these peaks tell you that this would be a two-step mechanism. There'd be some type of intermediate here in between those steps as well. So being able to look at these reaction coordinate diagrams, understanding, hey, look, this would be an exothermic reaction because the products are at a lower energy than the reactants. Being able to identify how many steps in the mechanism, the intermediate. You could even identify, hey, look, if this is your starting energy to get up to the peak, that would be your activation energy here for this particular one. So definitely be able to read these and get information from them. Just want to look at one more reaction coordinate diagram here. You can see the black line represents the reaction taking place with no catalyst. So you have your starting energy here of your reactants. There's a certain amount of activation energy, and then you get to your products here. Notice the activation energy, the EA, is measured here from your initial energy of your reactants up to the peak. So pay attention to that. You need to be able to realize that that would be your activation energy. And then this reaction overall would be exothermic because your ending energy is lower than your starting energy. So energy is exiting. But then notice in red, this would be your catalyst here. All right, same starting energy. But then if you notice, there's kind of a bunch more peaks there. This is definitely a different mechanism taking place. Remember, a catalyst speeds up the reaction by lowering the activation energy and providing a different pathway. All right, so the highest peak here would be this kind of third peak here. So the activation energy for this particular mechanism would be based on where you started up to that highest peak. All right, there are, if you look here, there's 1, 2, 3, 4 peaks. This would be a 4-step mechanism with a few intermediates in there. But just realize here that the activation energy would be based on the slow step, which would be the highest activation energy you see. So it's from kind of your starting energy here up to the highest peak would be the activation energy of the catalyst one. Realize here that the beginning and ending energy still the same for the catalyst. All right, it'd still be exothermic, still the exact same value for the overall delta H or the overall change in energy here, but it provided a alternate pathway and it lowered the overall activation energy here.